there were some questions from the online participants regarding physical significance of Riemann tensor, Ricci scalar, Ricci tensor, etc. So, as we have been mentioning that Riemann tensor R mu nu alpha beta, its geometric significance is that if you take any vector v mu and if you parallel transport it along a closed curve C of lambda, then if the curve is sufficiently small that the area enclosed within the curve is sufficiently small, you can show that after this vector is parallel transported, remember what is the equation for parallel transport? dv mu by d lambda as you go along C of lambda. So, parallel transport equation is this, and if you parallel transport it along this curve and come back, when you come back you will find that the vector in general is not having the same component. So, this is v mu plus delta v mu, and this delta v mu is proportional to the Riemann tensor and the area element, the area enclosed within this contour, which will have indices alpha, beta, gamma and so on. Yeah. So, that is the geometrical significance of the Riemann tensor. The physical significance, on the other hand, is that if you have two freely falling geodesics, by freely falling obviously they are geodesics. So, if you have one observer moving along this geodesic parametrized by lambda, then another observer y mu which is also parametrized by lambda, then the separation y mu minus x mu, if they are sufficiently close, remember this is something very important, the y mu's and the x mu's, they are coordinates, they are not vectors, but the separation, if they are sufficiently close, then y mu minus x mu, we can call it delta x mu of lambda, that's a vector. And geodesic deviation equation tells me that d square delta x mu by d lambda square, where lambda is the parameter parametrizing the geodesic, is proportional to r mu nu. Proportionally there will be sign factor, I don't remember with the plus sign, minus sign and so on, and you will find that so, in other words, the physical significance of the Riemann curvature tensor is that if you have two freely falling test particles, then if they are close by, the vector connecting the two close by freely falling particles, that vector undergoes this. There's a acceleration which is well defined acceleration, and this acceleration is proportional to the Riemann curvature tensor. And physically yesterday we said that this is essentially when you go to Newtonian gravity, where G00 is approximately 1 plus 2 phi by c square, where phi is the Newtonian potential, you will find that this object is second derivative of the phi, which is the tidal force, tidal field of the gravitation. So, in other words, Riemann tensor physically is responsible for all the tidal acceleration. Now, there were questions about what about the physical significance of the Ricci tensor and the Ricci scalar. That comes about when you write down the Einstein equation. I am told that in the morning session TP obtained the Einstein equation from differential geometry point of view. In coordinate frame, the Einstein equation can be written as r mu nu minus half g. We will actually obtain it in a different way. I don't know whether I'll be able to complete, at least by tomorrow it should be completed. So this is the celebrated Einstein equation, whose physical import is that if you give me the energy and momentum distribution of matter, then by solving this Einstein equation, so the right side contains the energy and momentum of the matter, then there are these Newton's constant capital G, and there is the speed of any zero rest mass particle, that is c, while the left hand side has all geometrical quantity. R mu nu is the Ricci tensor, G mu nu is the metric tensor, R is the Ricci scalar. So left hand side is geometry, right hand side is matter along with the physically significant Newton's gravitational constant and speed of zero rest mass particle, and this tells you that we are talking now about a relativistic theory of gravity, because capital G is appearing, so it's gravitational theory, C is appearing, means it's relativistic theory, and Einstein's equation tell you that you give me the energy and momentum distribution of matter, and I will tell you what is the geometry of the space-time by solving this equation. Remember, R mu nu, yesterday we saw R mu nu by definition is take the Riemann tensor and contract the upper index with the second index below, mu nu, so mu nu, and the scalar curvature is just trace of R mu nu. And because the Riemann curvature tensor is first derivative of the Christoffel symbol and also gamma gamma, the quadratic terms are also there. Therefore, and yesterday we saw that if you assume G mu nu semicolon alpha is 0 everywhere, then you can solve for the Christoffel symbol in terms of the metric and the partial derivatives of the metric. So therefore, the Riemann tensor, where is the Riemann? Yeah, Riemann tensor has second derivative of the metric, is constructed out of the second derivative of the metric as well as quadratic terms. Hence, the Einstein equation contains second derivative of the metric tensor and quadratic terms, because unlike electromagnetic theory, Einstein's theory is nonlinear. It's nonlinear in metric tensor. If you solve this equation, given energy and momentum distribution of matter, it's a second order differential equation in the metric. If you solve, you will get your metric tensor, provided you give me the metric tensor on spatial coordinates at one given time, and similarly first derivative of the metric tensor on the spatial section at one given time. You use the Einstein equation to solve for the metric tensor everywhere for all time. So you know the metric tensor for all times everywhere, and then you can compute the Riemann curvature tensor, Ricci tensor, Ricci scalar everywhere for all times. So it's a well-defined physical problem. When does the problem not work? If there's a singularity. If there's a singularity, the Riemann curvature tensor blows up, then you no longer can evolve your Einstein equation. That we know. I mean, that's what mathematicians call singularity. When things blow up to infinity, you no longer can solve the differential equation. And that's the reason why singularities are bad for a theory, because by now you must have understood physical theories are made of differential equation which preserves causality. Because what is cause and effect? You give me a cause, the effect can be predicted, and differential equation ensures it. Mathematically, cause and effect are the cause is the initial value and initial derivative, and the effect is by solving the differential equation we have the effect. That's the reason why all physical theories, the laws are in terms of differential equation. The only last thing I would like to point out, yesterday there were discussions about Weyl tensor. You can obtain Weyl tensor from the Riemann curvature tensor by subtracting the Ricci tensor, and I have the expression in my notebook. If someone wishes, I can give you the full expression, but this is nothing but your Riemann curvature tensor, and then you subtract from this terms which are R, mu, nu, and antisymmetrized combination of G's, etc., and similarly minus R, antisymmetrized combination of G, G, etc. Okay, and such that when you subtract the trace part, you will find that this object is 0. That means you raise one of the index, the C is the Weyl tensor, it's called the Weyl tensor. So if you try to contract the upper index and the second index, it will be 0 because you have removed the trace part. On the other hand, for the Riemann tensor, when you contract the upper index with the second index, you get the Ricci tensor. You have suitably subtracted out so that this is 0. And now let's come to physical significance of the Weyl tensor. Note that the tidal forces are given by the Riemann tensor. So outside a gravitating body, okay, before that I must come to Einstein's equation. Einstein equation can be also recast. We will do it again when we complete the derivation of Einstein equation from Einstein-Hilbert action. You can show that this can be also rewritten as where T is the trace of the energy momentum tensor. What this tells me is in the region where there is no matter, that means in the region where matter is absent, T mu nu and T will be 0, and therefore Einstein equation forces the Ricci tensor to be 0 in the region where there is no matter. If the Ricci tensor is 0, Ricci scalar is also 0 because Ricci scalar is just G mu nu R mu nu. And this tells me that if you are looking at the geodesic deviation, that means if you are looking at two test particles following a geodesic and you want to find out how the separation is changing with time, outside any matter distribution, because R mu nu and R are 0, outside the Weyl tensor is same as the Ricci tensor. So tidal acceleration between two test particles where there is no matter is determined by Weyl tensor, because outside the Riemann tensor and the Weyl tensor are identical because by virtue of Einstein equation. R mu nu and R are 0 where there is no matter because of this equation. All right, I think I have answered all the questions that were raised yesterday. Now I will talk about energy momentum tensor. Yesterday
I want to interrupt
Yeah, yeah.
So you said you transport a vector along a curve, right? And you
Parallelly transported.
parallelly transport, but you're not getting the same vector. You're getting plus delta.
If the Riemann tensor within the contour, if the Riemann tensor is non-zero, then you will not come back. Yesterday, I showed in the afternoon, I gave a specific example of parallel transporting a vector on the surface of the sphere and showed that indeed it doesn't. I'll show it again because you were not there probably in the afternoon discussion session. So consider the S2. S2 is the surface of the sphere and the equator is a geodesic, the longitudes are the geodesic, so there is a north, there is a south. So draw one particular longitude, draw another longitude which makes 90 degree here, so this is 90 degree and therefore longitudes at the equator will be 90 degree, okay. Consider this triangle on the curved space. So this is a triangle on the curved space because this is geodesic. And consider the vector here, parallel transported along this curve. Parallel transported meaning what? Here the vector is making angle 0 to the tangent vector to the equator. So when you parallel transport, it should continue to make angle 0. So parallel transport, here when you come here, the vector is this, okay? It makes 0 angle. Now you parallel transport along this. Here what angle it makes to this curve is 90 degree. So parallel transport 90 degree, come here. Parallel transport, this is 90 degree. Now again parallel transport, again for this curve it makes 0 angle. Parallel transport, when it comes here it is this vector. The original vector was this, parallel to the 90 degree. And you can show that it is nothing but because the Riemann tensor enclosed within this triangle is non-zero, you have.
So when we write this delta V mu proportional to the Riemann tensor in the
this result is exact when your loop area is sufficiently small.
Why area has 3 log and this is
No, not 3, sorry. And V gamma.
yes.
There's a V gamma also. Correct. Good that you pointed out. Okay. Now I will go back to the discussion on energy momentum tensor. Yesterday we talked about what is the physical significance of T mu nu. We said that T00 is the energy density, then T0I is the energy flux in the ith direction, which is same as momentum in the ith direction because energy moving in a direction constitutes momentum, and Ti0 is ith momentum component of the ith momentum density. Tij is the flux of ith component momentum in the jth direction. Now you can prove that your energy momentum tensor T mu nu better be symmetric if you want angular momentum to be conserved. I will not prove it. So angular momentum conservation, because how do you define angular momentum? So angular momentum is defined m mu nu angular momentum tensor. This is the orbital angular momentum, so it's integrated over space, is defined to be something like this. I mean, integrated over the spatial 3 surface. Okay. And you can prove that in flat space-time, if you take flat space-time, then distribution of matter, isolated distribution of matter, total angular momentum must be conserved, and you can prove that conservation of angular momentum demands that energy momentum tensor. We are talking about flat space-time. In flat space-time, angular momentum conservation requires that T mu nu must be T nu mu. Okay. And therefore, in curved space-time, again T mu nu better be T nu mu, because principle of equivalence principle. You go to any curvilinear coordinate system, if there is a tensor in flat space-time, it must be a tensor in arbitrary coordinate system. And symmetry properties of tensor are maintained no matter what kind of coordinate system transformations you make.
So what do you mean by energy momentum tensor in flat space?
Yesterday we talked about particles, free particles moving about. No, fluid. If you have.
That is no longer flat, right?
No, wait. This pre-general relativity. In pre-general relativity, when people did not know that energy and momentum curve the space-time, people talked about flat space-time, the energy momentum tensor of electromagnetic fields, they talked about it. So you can, in post-relativity, you can say that we are talking about test particles in a background geometry, and assume that the test particle's energy momentum tensor is not large enough to distort the background geometry. So in that sense, you can think of energy momentum tensors of test particles in flat space-time. Yeah. Right. So the bottom line is the energy momentum tensor better be symmetric in order angular momentum for an isolated system is conserved. Now comes a very interesting point. In field theory, okay, but before that some background. We all know from our classical mechanics exercise that whenever there is a symmetry, there is conservation law. So for example, if the Lagrangian doesn't change under translation along the x direction, then momentum along x direction is conserved. And if it doesn't change under any translation, x going to x plus delta x, y goes to y plus delta y, z goes to z plus delta z, then whole momentum is not conserved. Similarly, if the Lagrangian doesn't change under time translation, energy is conserved. These are something we prove in our mechanics course. But then the general proof is by Noether. Noether said that no matter what system, fields, particles, doesn't matter. Everything is given by an action principle, and the action is given by 1 over c integral of a Lagrangian density d4x. 1 over c because d4x will have dx0, dx1, dx2, dx3, and dx0 is c dt, and because action is L dt integral, so you divide by c. So in general, action is 1 over c Lagrangian density. I am talking about flat space time now again. Lagrangian, which will be function of the fields, particle trajectories, etc., doesn't matter, and d4x. Now Noether proved a very powerful theorem which said that if your action does not change under any transformation of degrees of freedom, so if it's made out of phi i's and derivative of del mu phi i's, then if the Lagrangian density, which goes to L prime, so this is of phi comma mu, and this is of phi prime, del phi prime, del x prime mu, Lorentz transformation. I am not talking about curvilinear coordinate system, such that this is same as L, then there are conserved quantities. It's called Noether theorem. It's a generalization of what we show in mechanics, that spatial translation leads to conservation of momentum, rotation concerns conservation of angular momentum, etc. And there are conserved current density. So if J mu, a generalized current density exists such that del J mu by del X mu is 0. That is what is Noether theorem, whenever there is such a symmetry. So Noether's powerful theorem linked immediately the notion of symmetries in gauge theories and conserved quantities. Yeah.
Sir, if you have just given the Lagrange, like half s dot square plus some potential, normal Lagrange like in the normal books are given, and if you have to find whether it's symmetric, it has momentum, angular momentum conservation, how would we find that?
Yeah, so rotation. So if you are Lagrangian is half m r dot product r dot v of some potential x, y, z. I'm not putting t because if I put t, energy is not conserved. Okay, let's say potential is independent of time explicitly, energy is conserved. Now in this, if v depends upon x, y, z, there is no translation symmetry. Linear momentum will not be conserved. But supposing v is such that when you rotate the axis, coordinate axis, the Lagrangian is invariant. This part is invariant, r dot, it's a dot product of two vectors, under rotation it will not change. But if Vx comma yz is such a function that under rotation of coordinate system is invariant, then angular momentum will be conserved. And what is the general result? That Vx comma yz is a function of V of r, where r is square root of x square plus y square plus z square. Then under rotation V of r goes to V of r, and you can prove that all the components of the angular momentum are conserved. Because you can always, how do you prove it? One component in the generalized coordinates, if you go to spherical polar coordinate system, this Lagrangian can be written as half m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus V of r, if there is a spherical symmetry. And you can immediately see there is no dependence of phi. So angular momentum is conserved. What is the angular momentum for this? The p phi, by definition, canonical conjugate is del L by del phi dot. And del L by del phi dot will be, if you differentiate it, you will get m r square sine square theta phi dot. So this, you can convince yourself that this is the angular Lz component. In Cartesian coordinate system, this is the Lz. So you have proved directly that Lz is a constant of motion. Because the Euler-Lagrangian equation is nothing but d by dt of p phi minus del v by del phi. That is del L by del phi, which is minus del v by del phi is 0. But del v doesn't depend upon phi. So d by dt of p phi is 0. There is an instance of Noether theorem. Hope you have got it. And because it is rotational symmetric, I could have called anything as my z-axis. So this immediately proves all components of the angular momentum are conserved. So this is the power of mathematics, that you can use symmetry to in one shot prove all components of angular momentum being conserved. Alright, yeah, so let me come back to Noether theorem. So now you say, very good, supposing my Lagrangian density doesn't depend explicitly on x, y, z. The way I have written it, it doesn't explicitly depend upon x, y, z, t. So there should be conserved current. The answer is yes, there is a conserved current, and it turns out the conserved current is the energy momentum tensor. So basically what I am saying is Noether theorem, that under the transformation x mu go to minus x prime mu, which is x mu plus del x mu. I am still talking about flat space-time. These are my Cartesian Minkowskian coordinate system. And if under this L is invariant, then you can construct T mu nu, which is conserved. But if you apply the Noether way of deriving T mu nu, you will find Noether way of deriving T mu nu doesn't give you a symmetric T mu nu. Okay? You can give various instances. I will not give the instances because that will take away time. But you must do it because there is something very mysterious about what I am going to say. So in other words, you try the quantum field theory manner of deriving the energy moment tensor. Because quantum field theorists, standard quantum field theorists, they will do quantum field theory in flat space time. And you will find that the T mu nu that you derive from Noether analysis, that T mu nu doesn't come out to be symmetric. But just now I said that for conserved angular momentum, you need T mu nu to be symmetric. So what the quantum field theory guys do, they add something called a Bell-Infante tensor. And they make it symmetric, and conservation is assured by adding something. You the local conservation T mu nu del x mu. Now what you have done is you made it symmetric by adding a term. Now it is T prime mu nu, and you ensure that your new energy momentum tensor which is symmetric satisfies the conservation law. Conservation law is this.
So any reason we can think of physically why it is not symmetric in general?
No, so Noether's way will never give you in general symmetric tensor. You know the Noether way of getting it, right? Noether way of getting it is using this, that your T mu nu, you add P mu nu x dot mu minus L times eta mu nu. That is how you generate your by extra, any general field is this phi dot mu. Yeah. So phi dot mu and del L density by del phi dot nu. That's your Noether way of obtaining the energy momentum tensor. You can show it's conserved. This is symmetric, but this is not in general symmetric. So you add a Bell-Infante tensor by make it symmetric, and the Bell-Infante tensor is constructed in such a way that this part is maintained. The local conservation, still you get it. Okay. Now, interesting part is, I am told that is due to Hilbert. Hilbert developed another way of getting the energy momentum tensor, that I will do now, where in one shot from the Lagrangian density you get a completely symmetric tensor, and when you apply it to the flat space time you have a conserved element symmetric energy momentum tensor. What is the link between the two methods is still not known. That means, why does Hilbert's thing work? It works, but what is the deep aspect? At least I don't know what the deep aspect. I mean, when I was a graduate student, I spent some time thinking, but I have not found a deep reason why Hilbert's method gives you the correct symmetric energy momentum tensor. But first, let me tell you what is Hilbert's method of getting the energy momentum tensor. Okay, I'll erase that part. So, power of pure mathematics is illustrated by Hilbert's method. It's magical, it's simply magical. Hilbert's method of obtaining energy boundary. So, of course, Hilbert's method starts with arbitrary coordinate system. Doesn't matter about whether there is curved spacetime or not. Curved spacetime is when Riemann tensor is non-zero everywhere. But we can just start with arbitrary coordinate system and we'll assume that there is a metric and therefore the action for the matter. So action for, I'll put a subscript m stating that it is matter. The action for the matter will be 1 over c Lagrangian density of some field variable. So let's call the fields phi a's. So these are my phi a's field, they depend upon x, and derivatives of covariant derivatives. So we are not talking about curvilinear coordinate system. So we will have covariant derivatives. That means what? That you will have phi b's of x and its derivatives, partial derivatives, and because covariant derivatives have derivative with respect to the metric, so therefore there will be a metric g mu nu and derivatives of the metric g mu nu semicolon alpha. And there is root minus g d4x. I will tell you why we have to have root minus g d4x. First, let's look at this expression. L is our Lagrangian density in arbitrary coordinate system, and L for the matter field will be functions of the matter degrees of freedom phi a and derivatives of the matter degrees of freedom, and of course the metric tensor and the derivatives of the metric tensor, because you see your Lagrangian density must be a scalar quantity. For scalar quantity you better have covariant derivatives of the matter fields. By the way, you can say that does it work for the point particle? The answer is yes. The point particle also works, because if you take a single point particle, then action for a single point particle is rest mass c square root of g mu nu xs dx mu. I can put it as dt dx nu some coordinate time dt into dt. Alright. So this is my action and therefore this is my Lagrangian. But I can write it as a Lagrangian density by doing this trick. So call the particle, so particle, label the particle as A. So this is for the Ath particle, this is my action, and so therefore so now you see dt d cube x, so this can be written as multiplied by c, so this is minus m integral a Lagrangian density d4x where the degrees of freedom are xa mu and x dot mu. And in this, of course, there is no derivative of the metric, just g mu nu is there. So I have got a Lagrangian density exactly like this. So even point particles, you can write it in terms of Lagrangian density, and Hilbert's method, you can apply it to that also. Okay. Oh, by the way, I made a mistake. No one pointed out. So remember, I have to put a root minus g. So if I put a root minus g here, I have to divide by a root minus g. Why root minus g d4x? Remember, if Lagrangian density is scalar and action is scalar, I must have the volume, 4-dimensional volume element, that must be also a scalar. But we know that under a general coordinate transformation, so if I make a general coordinate transformation, x alpha going to x prime alpha, how would d4x transform? d4x prime will be the Jacobian. What is Jacobian? Determinant of del x prime mu by del x alpha into d4x. There's something we have been doing it all through when you go from Cartesian coordinate volume integral to spherical polar coordinate system volume integral. Remember, what are the examples? Supposing I have something integrate dxy, dyz, dz. But when you go to spherical polar coordinate system, it will be dr, d theta, d phi, but there is a Jacobian which is r square sine theta. Okay. So this part comes from the Jacobian. Okay. All right. So therefore, d4x is not same as d4x prime. There is a determinant of the partial derivative by x prime with respect to x, and hence we have to multiply d4x by a quantity which remains invariant, so that action remains invariant. d4x changes, this doesn't change. I have to multiply to d4x some quantity which cancels the Jacobian, because d4x prime is Jacobian into old d4x. And what is that quantity? It is root minus g. Why? Because consider g mu nu. Under a coordinate transformation, g mu nu will go to g prime mu nu, which is by definition, it's a covariant metric tensor. It will be this. G alpha beta. Note, here it is del x prime mu by del x alpha, while metric is del x alpha by del x prime mu and all that. And hence, the determinant g mu nu goes to determinant g prime mu nu, which is nothing but, you view it as a matrix, then it turns out this is 1 over j square. If that is j, if this I call it as j, then this is 1 over j square, determinant of g alpha. Okay? Well, there are two objects. This is a matrix, there are two matrices. That's why 1 over j square. Why 1 over j? Because this is del x alpha by del x prime mu, that was del x prime mu by del x alpha. So convince yourself, it's very simple. You just have to treat this as a matrix. You can show that. And therefore, and I will, by the way, determinant of g mu nu is defined to be this quantity g. Is there a notation? So therefore, what we have proved is g goes to g prime, which is equal to g divided by j square. And remember, we are talking about a Lorentzian space-time. The metric determinant is negative. Whether you take the metric signature plus, minus, 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 or minus, plus, plus, plus. So in the Lorentzian case, that is our space-time is Lorentzian. So therefore, determinant is negative, and therefore what you do is you say, okay, if that is the case, root minus g goes to root minus g prime, which is equal to root minus g by j, mod of j out, and therefore root minus j d4x is invariant, and that's the reason why when we are dealing with Lagrangian density and action in curvilinear coordinate system, we put root minus g d4x. All right. So mathematicians developed this whole business of calculus of variation. People like Hilbert, Courant, they played a very important role in developing the field of calculus of variation for the fields. Of course, Lagrange and Euler did it for point particles, but for the fields, Courant, Hilbert, they developed the entire machinery of calculus of variation. Now Hilbert said this, all right, this is for any system, physical system, I can write down my action in terms of a Lagrangian density. So therefore I can, shorthand will be 1 over c L root minus g d4x. This my action for any system of matter distribution, any, whether it's point particles, whether electromagnetic fields, whether scalar fields, and what have you. Now Hilbert asked the following question, that this is true given a metric. Suppose I want to understand how does the matter action changes when I make an infinitesimal variation in the metric. So what I am saying is, now suppose I take a new metric g bar mu nu, no coordinate transformation, same coordinates, I am not making any coordinate transformation. But I ask, instead of using the old metric g mu nu, suppose I did the calculation using a new metric g bar mu nu, which is old metric g mu nu of x, plus a tiny variation, delta g. How will the action change? That was a question that Hilbert asked. So obviously with this, you have different a prime m. So again, let's write down, because these are, if someone is encountering, so this is when you used the metric g, and this is when you are using g bar. A prime is with g bar. Then by definition, this will be 1 over c del L of phi a will not change, del phi b by del x mu will remain same. It's the metric that will change, g bar mu, and derivatives of g. So no coordinate changes, only the metric that is being set. So therefore determinant will change, root minus g bar before x. Okay, so I'll go to the other part of the board. Yeah. Good. So therefore you say delta g mu is an infinitesimal variation in the metric. You say therefore what is the variation in the action am, which by definition is am prime, which is with metric g bar, minus am, which is with metric g. And this is, if you look at this, there is no coordinate transformation, d4x is same, the change will come from this, the change will only come from this, and therefore this same as 1 over c integral variation in L root minus c. Remember, we are making infinitesimal variation. So we will retain only first order terms. That's the trick which we have been using again and again. We are only using infinitesimal variation. If it is an infinitesimal variation, this is nothing but pure calculus. There is nothing but partial derivative of with respect to, I am wearing G mu nu, del G mu nu. But Lagrangian density root minus G doesn't have derivative of the metric, but the Lagrangian density has derivative of the metric. Why? Because there you have the covariant derivative, and covariant derivative has Christoffel symbols, and Christoffel symbols will have derivatives with respect to metric. So therefore this is also, there should be another term, del of by del of del G mu nu by del x alpha delta of del G mu nu by del x alpha. Okay. Now some mathematical identities. This is something which is we do even in classical mechanics. So I can do it here. Very often when we first encounter in classical mechanics, I remember when I first was being taught Goldstein, I was said, oh, is it something very new? Then found out, no, it's a trivial thing. Very often you say when you are doing variation that del qi dot is same as d by dt of del qi. Okay, it sounds very, very mysterious. It can, it's just, it follows. I'll show it for a general case. So we have that result. What is del of del G mu nu by del x alpha? This is nothing but, by definition, what is del? What is del G mu nu? This is the main thing. So therefore, del G mu nu by definition is G bar mu nu minus G mu nu. And therefore, del of G mu nu by del x alpha by definition is del G bar mu nu minus del G mu nu del x alpha. Okay. But del by del x alpha is a partial derivative, is linear. So this can be also written as del by del x alpha of G bar mu nu minus G mu nu. But G bar mu nu by G mu nu is delta G mu nu. So this is same as del by del x alpha of del G mu nu. In other words, which appeared when we were doing classical mechanics mysterious, that variation del commutes with derivative with respect to time. This can be derived exactly the same way. So therefore, del of partial derivative G mu nu commutes with partial derivative. This is the proof. But it's not an assumption, it can be proved. I have just proved it. So, yeah.
Is this applicable to any general theorem G?
Say that again.
Is this applicable to a
Any G mu nu, any scalar field. So when you do the equation of motion, if you vary phi, delta phi, then delta of del phi by del x mu is also del by del x mu of delta phi. Exactly the same proof. Okay. So therefore, this object delta of del G mu nu by del x mu is same as del by del x alpha of del G mu. Just now I proved it. Okay. Now let us look at this term, this piece. Just this piece. Let us look at it. One over C del L root minus G by del of just the last term. I am just looking at the last term. Yeah. Now this term I can rewrite. Here the partial derivative is acting on gel mu nu. I want to take partial derivative on this, but which is same as I first take the full partial derivative of d4x, but this is equal to, I have to subtract a term, that means del G mu nu as it is, this acting on this. I have to subtract that term. Everyone agrees with this? That this is identical to this because of the Leibniz property of the derivatives. Okay.
Can't the second term be written as the dou square?
What?
Is it okay to write it as dou square of
Dou square? No, because this derivative of the Lagrangian is theta. Oh, this is not bracket. It's just here the bracket is not there. Bracket. It is the partial derivative with respect to this function. Is not with respect to coordinates. Okay. All right. Now the magic happens. What is the magic? Remember, alpha is being summed over. Gauss's theorem. Gauss's theorem in now 3 plus 1 dimension. This is like divergence. In 3 dimension, it was a 3 dimension, it would have been divergence of something d cube x. The divergence of something can be written as del by del xi of something I summed over. Here also del by del x alpha, G mu nu has been summed over, but there is a del by del x alpha. So it's like divergence, and divergence tells me that the 4 volume now, This is nothing but surface integral. Now it has an index alpha. Whatever that has an index alpha, it is over a three-dimensional hypersurface. This was a four-dimensional volume, three-dimensional surface, hypersurface, which goes to infinity. Because this volume integral over was all space-time. If it is all space-time, delta G mu nu at infinity, the variation at infinity, must be 0. That constraint I should have imposed. That I have made a variation in the metric tensor such that at boundary the metric tensor variation is 0. Boundary meaning infinity. So at infinity, del G mu nu is 0. So therefore, this term, by virtue of the Gauss's theorem, which tells me this four-dimensional volume integral can be written as an integral over three-dimensional hypersurface whose area element is d psi alpha, because a three-dimensional element can be written, the normal to it is a 4 vector, just like the surface S2 surface, the normal vector is a three-dimensional unit vector.
So it basically is a sum of time boundary and spatial boundary, right?
Yeah, everything, full thing. Space is going to infinity, time is also going to infinity. And at infinity, the variation delta G mu nu is 0. That restriction I should have imposed. Then this integral goes to 0. So this integral goes to 0 by virtue of Gauss's theorem. And therefore, finally we get that this quantity is simply negative of that, and I'll substitute back in this equation. And hence we get that the variation in the matter action due to infinitesimal variation in the metric tensor is simply this 1 over c. Now you see that delta G mu nu can be taken common. There is a delta G mu nu, there is a delta G mu nu here. We can take it common. Now there is a negative sign. So this part is 0, so negative sign. T4x. There is a variation in the matter action due to infinitesimal variation in the metric tensor. Now I will erase this part of the board. Now there is a sign convention. I always forget the sign convention, so let me refer to my notes. Okay, so yeah. The sign convention is that this is defined to be, so Hilbert defined it to be yeah. So what Hilbert said is this entire quantity inside the bracket, there's a delta G mu nu etc. But this entire quantity in the bracket is half T mu nu into root minus G. So in other words, Hilbert said that the energy momentum tensor T mu nu is nothing but 1 over 2 root minus G so let's see, this is this, yeah, 1 over 2 root minus G multiplied by this thing del of okay. So Hilbert did pure mathematics given a matter action. Physics is where? Physics is here. Physicists gave me a matter action in flat space time. Hilbert said, okay, I'll choose any arbitrary coordinate system. So, go to the process. Physicists don't know about general relativity or didn't know about general relativity before Einstein. Physicists they knew special relativity. So they gave Hilbert, or Hilbert took, whatever way you think it about it. So they gave Hilbert in flat space time whatever the matter action is. Yeah.
Is there any physical motivation was there for Hilbert to choose this as a energy momentum tensor?
I don't know. I don't know why Hilbert identified. Probably Hilbert would have taken case by case. Mathematicians, mathematicians approach. They say, does this happen for this prime number 3? Does it happen for the prime number 5? Does it happen for the prime number 7? Does it happen for prime number 13? If it happens, induction. It must be valid for all prime numbers. So Hilbert might have said, okay, does it happen for a point particle? Does it happen for electromagnetic fields? Then he would say, if it happens, if it is true for electromagnetic fields, for collection of point particles, I will now generalize. Oh, it's so generalized.
So is there a half factor mismatch, like if you define your premium like half?
Huh?
Half factor, is there a mismatch of half factor?
Let me see. Let me check numerical. Because these are convention, I have to see whether I have stuck to the convention. So according to my notes, this 1 over c, this factor is 1 over 2c T mu nu. Yeah, I think this is all right. This is all right. This is all right. You can check the internet and all that, books.
So I was not, we started with the Lagrangian which are scalar things as a dynamical variables along with having G mu nu as a dynamical variable.
No, at the moment we don't know whether G mu nu is a dynamical variable. G mu nu has been installed. If I use different curvilinear coordinate system, there has to be a metric. That's all. Whether G mu nu is a dynamical physical field, No assumption has been made.
But we are varying with respect to it, which means it is
No, I am varying with respect to change of metric. But whether metric has any physical significance, I don't know. I better need to put metric because I have chosen a arbitrary curvilinear coordinate system. If I choose arbitrary curvilinear coordinate system, I need a metric to tell me what are the invariant proper distances. I need to have a notion of Christopher symbol, otherwise I don't know how I can take the derivative of a vector field. But I can just say that the metric tensor is a bookkeeping device, just like the Euclidean metric tells me how to find out distances between 2 points xyz and x plus dx, y plus dy, d plus dz. But then if I change my coordinate system, then I better have my metric going from 1 1 1 1 to 1 r square sine square theta. These are bookkeeping devices.
but the doctrine actually different. When I'm writing the Lagrange, I write down all the dynamical variables that are not with respect to
No.
varying.
What are the dynamical variables here? Matter.
Yeah.
Geometry, I don't know. Geometry, I am keeping it as a bookkeeping device. Matter, we know, is electromagnetic field, scalar fields, Dirac field, point particle degrees of freedom. These are my dynamical variables.
If I vary with respect to phi, I will get the same.
Wait. I am not varying with respect to phi.
That's what I'm asking. But that would also give me a d mu.
No, that will give me the equation of motion for the phis. If you did variation with respect to phi and demanded that delta am is 0, you will get the equations of motion. I am not even demanding delta am is equal to 0. That is the point. I am not demanding that under the variation of the metric tensor delta m is 0. I have not demanded that. What you are saying is, if I had taken the action for a dynamical set of field, did a small variation in the dynamical variable fields and demanded that action goes to 0, I would get Euler-Lagrangian equations for the fields.
Here we are getting p mu by varying.
Here I have not varied the dynamical degrees of freedom, which are the phis. I didn't vary. See, variation was never done for phi a's. The variation was done only for the metric. See how out of box Hilbert is thinking. Hilbert knows about Euler-Lagrangian equation of motion, where Noether theorem has already been imposed. Good that you are asking this question. These are very subtle points. So again, her question is very important. If I have an action for any fields, whether it is point particles, electromagnetic fields, scalar fields, if I know the action, how do I know the dynamical equations for those fields? What I do is, I'll say vary the fields and demand under infinitesimal field variation action delta A is 0. Why? Because least action principle. That the fields evolve in such a way that action is an extremum. That means under infinitesimal variation of true equation of motion, the first order variation action must be 0, and you get your Euler-Lagrange equation of motion. So I shouldn't be talking in the air. We should be exactly take an example. So take the action for the free electromagnetic field. I know for the free electromagnetic field there are this 4 pi minus 1 over 4 pi f mu nu, flat space. I am talking about flat space. This is the action for the electromagnetic field. How do we get Maxwell's equation? We say that make the variation a mu going to a prime mu plus delta of a mu. Okay, and demand that under infinitesimal variation a mu, if the electromagnetic fields were evolving according to true solutions a mu, then if I make infinitesimal but arbitrary variation, then delta of AEM must be 0. That means what? So that means that I'll not minus, that means delta of f mu nu integral d4x is 0, and then you can show that this is all del f mu nu by del a alpha, delta a alpha plus, I mean, same thing to be done for f mu nu upstairs also, by del a alpha by del x beta, del of all that, and same thing for upper thing, and set it to 0, you get your Maxwell's equation. So note the difference. I did not do variation in the matter fields. I did an infinitesimal variation in the metric tensor, and I said when I did that, the infinitesimal change in the matter energy moment tensor, I got it to be this. And Hilbert now assures me that whatever is there in the square bracket is half T mu nu into root minus G. So that T mu nu is this.
Would we have arrived at the same conclusion if we vary both the dynamic variables?
I'm not doing that. I'm not doing that. I'm not doing that. I'll tell you what will happen then. I'm not doing that. First, we only varied the metric tensor, and then Hilbert assures me that whatever I have got is the energy momentum tensor. It's pure magic. Someone will come and say that, look, I didn't know about, I don't know about generating. I only deal with Minkowskian coordinate system, and I know, and you have brought in G mu nu. What are these? Hilbert will say that, look, you used the Minkowskian coordinate system x, y, z, ct. I say that, look, I am not interested in I'll make mathematical transformation. Whether they have any physical significance or not, I have no idea, but I will do that, and eta mu nu will go to some quantity which I call G mu nu as eta mu nu del x mu by del x prime alpha del x nu by del x prime beta. I will call that my metric. Whether it corresponds to physics, I don't care. I am just doing mathematical analysis, and I do that. I get for you the energy momentum tensor, and you are saying, but the real world is flat space time. What do? Don't worry. Wherever you have G set to eta mu nu, wherever you have that, do it after deriving all this, and you will get your flat space energy momentum. And lo and behold, you get it. And it is assured that your energy momentum tensor you have got is symmetry. It's pure magic. How it corresponds to Noether's way of getting energy momentum tensor, what is the link? As a graduate, later on I didn't bother, but as a graduate student, I bothered about it. I have not found the solution. Okay? Yeah?
When we are working with the Hilbert action and when we vary with
No, that will be, okay, what is the time? So I will start it, that I will complete it tomorrow. I have not talked about the gravitational degrees of freedom as of now. I am only dealing with matter.
In that case, the metric is being interpreted as a dynamic.
We'll come to that. I will come to that. But before that, lot of machineries have to be developed. I like developing a subject the mathematician will develop, state all the assumptions. So we'll do that. But first, let's agree as to what we have obtained.
Is this then the Lagrangian that we're taking minimally coupled so that we don't
Nothing. No minimal coupling assumption, absolutely nothing. All we have told is that whatever curvilinear coordinate system you are imposing mathematically, you must have your Lagrangian density to be scalar. That's why root minus g you have to better put in, because d4x transforms, root minus g d4x is a scalar under general coordinate transformation. That's what I have erased that part. That's what I have argued. Okay, so let me state it again. What has Hilbert done? A physicist came to Hilbert, said that, look, I know my physics in special relativity case thoroughly, and like electrodynamics or material particles, free particles moving, I know all that, and therefore I know their Lagrangian density, and therefore I know the action in flat space-time, and I want to know its energy moment tensor, and there is a way, Noether's way. Noether says that if you make infinitesimal translation, that means my Lorentz coordinates x mu goes to x mu plus a mu, where a mu is constant. By the way, if you do the Noether way, you will find that you don't take a mu to be constant. You take a mu to be space-time dependent. That's also another mysterious thing. But there is a better way done by Landau-Lifshitz for flat space-time energy moment tensor in classical theory of fields. That's a much better way. Anyway, then when you obtain that way the conserved energy moment, you'll get something. You will get a T mu nu, let's call it theta mu. That's what quantum field theory people will say. You'll get a theta mu nu from that analysis by imposing that under x mu going to x mu plus a translation, but you make it space-time dependent. That's the Isgisen-Zubair method. If you read Isgisen, and you'll obtain from Noether's theorem a theta mu nu which satisfies del theta mu nu by del x nu equals 0. That means local conservation of energy moment tensor. But in general, you will find theta mu nu is not equal to theta nu mu. But Belinfante will come and say, no issues. I will add a term which is antisymmetric at two indices such that I add to it theta bar I define, which is theta mu nu plus a Belinfante tensor, and suitably something del by del x alpha or something like that, such that when I take the derivative, I'll get del 2 by that derivative to be 0. You have to be clever enough to choose that Belinfante tensor. And then, but that did not follow from your Noether argument. You have to add by being slightly more creative. You added a term to the energy moment tensor. It didn't directly follow from Noether theorem. So how do you trust the Belinfante tensor? How do you know that you mathematically added a term saying that it makes but how are you sure that in real world that term constitutes the correct addition to energy moment tensor? There are no clue, there are no answers. Hilbert on the other hand said, well, I have developed a new method. I will treat as though I will treat flat space time, yes, but I'll use arbitrary coordinate system. And then in the arbitrary coordinate system, the metric tensor will no longer be eta mu nu. Remember, it is still flat space time. Even in flat space time, if you choose arbitrary coordinate system, you will have a Christopher symbol. Riemann curvature tensor will be 0, but Christopher symbol will appear. For example, in Minkowski space time, if you choose instead of the Minkowski coordinates, if you choose time to be time but space to be r theta phi, your Christopher symbols will not be 0. Then you demand that you gave me a flat space-time matter action. I chose curvilinear coordinate system, so there will be metric appearing, there will be Christopher symbol appearing. Now I will do something magical. I will say that I will not do any coordinate transformation, I will vary the metric infinitesimally. And what do I get? This is a out of box thinking. Because as a mathematician, I will say, oh yes, in the curvilinear coordinate system, I had a metric G mu nu. But I am just curious, what if I had chosen slightly a different metric? What would have happened? And then you go along doing that and say that finally it turns out that change in the action due to that variation is this, and I will call whatever is there in the box as half T mu nu root minus G. And then I'll claim that is what is my physical energy moment tensor. And the mysterious thing is, whether you use electrodynamics or point particles, you get the correct energy moment tensor. So I suggest someone to, I wrote down the single point particle, I wrote down its action. You use Hilbert's method and you'll find you get the correct energy moment tensor for a single particle. Weinberg of course does it for a whole classical, a whole system of particles. But even for a single particle is very interesting. He'll get back the correct energy moment. And I find it magical. Why is it true? Why does it happen this way? I have not figured out that subtle point. I think there is something in it deeper. And people are writing papers even today. Yesterday I was finding some internet thing. I find people are comparing Noether way of getting energy moment tensor, Hilbert's way of getting tensor, and they are talking about it. But there is something mysterious. Yeah, so, okay, now we will go to Einstein-Hilbert action. Okay. Okay, so I'll assume that I have covered the matter part. Now again go back to geometry. We would need more chalks. This is almost over. I think I single-handedly finished the entire box of chalks. Right. Now we return our focus to geometry once again. Okay, here, because geometry is fine, but we have to have a certain physical notions. Let us say, what are the physical dimensions of geometrical quantities? So go back to our notion of proper distance. So in arbitrary curvilinear coordinate system, we know metric tensor is that which gives me the invariant distance between x mu and x mu plus dx mu. ds square, now we are physicists, for us ds square is length square. So physical dimension, as you know, we physicists, when we say physical dimension, we put it in this bracket. Physical dimension of ds square is what? Length square. So my physical, by the way, this is also another very deep thing about physics. You can show all physical quantities, their physical dimensions are a combinations of length, mass and time, no other. So you can ask why? Why is it that all physical quantities that we know of, they carry physical dimensions which is combination of length, mass, time, their powers, and why? Someone will say, what about charge? Yeah, you think about charge, eventually it will be some combination of length, mass, time. So long time back when Rajaram Nityananda was visiting Bombay, he said that one student asked me and I didn't know what to answer. I pointed out to him that one solution is this, that we in laboratory, how do we designate physical dimension? Through measurement. Anything we measure in laboratory, what our ultimate measurement thing, we measure either length or we measure time or we measure amount of energy transfer, which is same as m. Any measurement will involve change in energy, change in length, change in time, change in energy is same as change in mass times c square. So therefore, These are the quantities you will have. Then I pointed out that if suppose there is an extra dimension, completely extra dimension, and we can move in the extra dimension, change it, then there will be an additional dimension. Anyway, I don't know whether I convinced Rajaram Nityananda. Paddy was also there during a long time back, in early 1990s we were having this discussion. Anyway, that's my idea, that's the reason why we have only 3 dimension. Coming back, we know ds square has length square. So suppose I choose my coordinates as that x mu's have dimensions of length, then so if physical dimensions of x mu is length, then g mu nu is dimensionless. Okay. All right. That immediately tells me that physical dimension of the Christopher symbols then if this is true, so if this is true, then physical dimension of Christopher symbol is what? 1 over L, because it's derivative. And all these tell me the physical dimension of Riemann tensor is what? 1 over L square. Now, we are physicists. For physicists, for any dynamical equations, we know we need the action. Because through Euler-Lagrange equations, we can figure out how the dynamical fields vary with time. So as someone said, that physics is where action is. Okay, so I retorted to that chemistry is where reaction is. Okay, so action is important. Okay, so we want to construct an action for geometry. So we want to have geometrodynamics. How we want to know. So what is the action for? The action for the geometry should also have the dimension of what? Action. What is the dimension of action? Yeah, same as dimension of Planck's constant, but in terms of MLT is action's dimension is energy into time. Energy's dimension is ml square by t square, kinetic energy. Energy into time, so time cancels. Action's dimension is ml square by t. Okay. Yeah. There also momentum into space. So ml by t is momentum into space. So ml square by t. This is the dimension of action. So we want to construct an action using geometrical quantities, and so first of all we want to construct the Lagrangian density. So we'll have to integrate over 4 volume into Lagrangian density so that I get ml square. So I want to know, remember, so the action for geometry G must be a Lagrangian density which contains metric and metric derivative, and in general second derivative also. Root minus g d4 should be there, because if this is a scalar, root minus g d4x is invariant under general coordinate transformation. And I want to know what this object is. So therefore my Lagrangian density, 1 over c, because d4x by c, because I need d cube x dt. Now dimension of Lagrangian density. If action's dimension is ml square t, what is the dimension of Lagrangian density? Remember, d4x has a dimension of L raised to power 4. d4x is L raised to power 4. L raised to power 4 divided by c, which is L cube into t. Okay, L cube into T. So Lagrangian density must have the dimension action by, so ml square by T divided by L cube into T. So that is nothing but m by L T square. So Lagrangian density must have the dimension m by L T square. So imagine that I am Hilbert and I hope, again there's a big controversy as to who gave the action. Some people say first Hilbert gave, then some people say first Einstein gave. Let's not go into all that. So we are trying to invent an action for the geometrodynamics. So I know that Lagrangian density must have mass by Lt square, physical dimension. Then I say that look, in my simplest of all theory, and Lagrangian density must be scalar. That much we know, it should be scalar. What is the simplest scalar I can think concerning geometry? What's the simplest scalar? Ricci scalar. So I should say that Lagrangian density, my simplest guess would be Lagrangian density for the gravity must be proportional to Ricci scalar. But Ricci scalar's physical dimension is what? 1 by L square. Well, Ricci scalar is by contracting G mu nu with R mu nu. R mu nu is 1 over L square. G mu nu is dimensionless. Ricci scalar has dimension of 1 over L square. So what should I multiply such that I get ml by T square? What should I multiply? It turns out, convince yourself, it turns out that I should multiply C cube by G. No Planck's constant. I better not use Planck's constant. I could have used Planck's constant, but I better not use Planck's. Why? Because I am talking about classical theory. Why should quantum thing enter? Okay. So then the Einstein-Hilbert action comes out to be minus C cube by 16 pi G R root minus G d4x. Okay. The 16 pi factor I have to put so that I get back in some limit, I get back my Newtonian gravitational equation that Laplacian of phi is 4 pi G rho. If I want to get that, I need the factor 16 pi. You might say, what about negative sign? Negative sign because the action must not blow to infinity. Okay. So R, curvature, you can make the curvature very large, infinitely large. So if it is positive, the action blows up to, I don't want that. So if I want everything should have well behaved, bounded thing, for that I need a negative sign. Alright, so from pure dimensional argument, from the fact that Lagrangian density is a scalar under general coordinate transformation, the simplest Lagrangian one can construct is this. Of course, people go for higher derivative theories like R mu nu, R mu nu. You can have R mu nu alpha beta, R mu nu alpha. You can think of all such combination. But you know, whenever you want to do that, you will find you need to put in additional parameters to make the dimension action must have ml square by t. So any other term, higher derivative term, modified gravity, which people work on, you have to have other parameters into it or put in Planck's constant. But the beauty of Einstein and Hilbert's approach was no new parameters were introduced. Absolutely no new parameters. The entire general relativity was constructed without introducing any new parameters. And the triumph of general relativity is that it solved already a problem that plagued astronomers, parallel precision, which Anuj, you have already discussed parallel precision of Mercury. The anomalous parallel precision, 43 arc second per century, was a puzzle for astronomers. Einstein explained that, and he predicted bending of light, which within few years of proposal of general relativity, the team led by Eddington confirmed it, because Newtonian bending of light would be 2 gm by c square b. General relativity predicts 4 gm by c square b. So there is a difference, and it was ascertained. Compared to any new theory in particle physics, general relativity was doing new prediction without assuming any new free parameter. That is the reason I think physicists say that general relativity is one of the most beautiful theory of nature. Absolutely no new introduction of parameter, purely from aesthetics. You create a theory and the predictions, early predictions, Pound-Repka experiment, all have been tested, and so far general relativity stands out uniquely because no observations have ever created a doubt regarding general. Yes, quantizing is a separate problem, and people therefore use all modified theories to get a good quantum theory of gravity. That apart. By the way, so I will, before I take up variation, now why did Hilbert introduce the variation metric? Now you are doing the field equation. Now the metric becomes dynamical. And just like Euler-Lagrange equation, I will vary the action with respect to metric to see how metric evolves with that. That apart, but first let me do some things to show that, first of all, let me point out one thing. I have varied with respect to lower mu news and obtained that. Someone will say, what if I vary upper G mu nu? Because I will be varying here upper G mu nu. So that I will make a connection and I will give a result for you to prove, so that I don't spend time proving that result. So before I stop the class, I will prove one important identity. Very often it comes very handy when we are doing our own research work. It is this. Remember that G mu alpha, G alpha nu, because the matrix inverse is delta mu nu. So if I do a variation in the metric, delta mu nu doesn't change. So therefore, delta of G mu alpha, G alpha nu is 0. Okay. By the way, you can prove, I didn't prove. Sometimes when we introduce covariant derivative, we will ask, what is the covariant derivative of the delta mu nu? Delta mu nu is a valid 1-1 tensor in curved spacetime. So try it out. Take the covariant derivative of connected delta, you will find 0. It better be 0, no? And it comes out alright. So that gives us confidence that the way we introduce the Christopher symbol is the right way. Anyway, anyone detecting a faint smell? Is there a... Okay. Anyway, maybe probably chalk dust smell. Anyway, so this is true. So this implies that the same as I'll use Leibniz rule for the infinitesimal variation. Yeah. So delta is an infinitesimal variation, so it must satisfy Leibniz rule, and therefore this is 0, and hence hence I get the result that G alpha nu delta of G mu alpha is minus G mu alpha delta G alpha nu. Let's see whether all the indices are in place. So G alpha nu delta G mu alpha minus G mu alpha, yeah, so this is fine. Now alpha is being summed over, but nu mu are free indices, so what I'll do is I'll multiply both sides by beta. Beta. Okay. But G beta nu, alpha nu, nu is being summed over is what? Nu is being summed over is delta beta alpha. So this is delta beta alpha. Alpha alpha is being summed over, Kronecker delta. So wherever there is alpha, I get beta. So I have got the identity that delta G mu beta upstairs is related to delta G alpha nu downstairs by this. Remember, it's not plus. It doesn't transform like a tensor. It's not raising and there's a negative sign. Okay. So in other words, because I have delta G mu, so therefore this is same as, now I am coming here, this same as 1 over C half T mu nu delta G mu nu. I have established there is a negative sign now, minus delta G mu nu is same as, oh, I should have gone the other way around. Doesn't matter, one can go other way around. I went, so from here I would have got G mu alpha delta G alpha nu is minus G alpha nu delta G mu alpha, and therefore by multiplying all that I will get mu alpha, and I want to multiply alpha alpha G mu beta You get the gist. All that will tell me that there is a minus, and del G mu nu can be written as, there is a minus sign, del mu alpha, del mu del beta, del G mu alpha beta. Okay? Convince yourself that del G mu nu is minus G mu alpha, G nu beta, del G mu alpha. And then of course root minus G d4x and all that. I want you to record, because when I do the Einstein equation, whatever I have written here will be reproduced. Okay? So therefore this is equal to, now note, what is T mu nu, G mu alpha, G nu beta? It's lowering of the indices. So this is same as minus 1 over C half T alpha beta delta G alpha beta upstairs root minus G d4x. Okay. So this result you have to remember, because when I do variation for the Einstein-Hilbert action, I'll have to come back here. The other thing I will tell you to prove is this. The Christopher symbol, when you sum up the upper index with the lower index, then this is same as del x mu of log of root minus g. It's a very simple proof. If anyone wants, we can discuss how you obtain. So take the Christopher symbol, sum the upper index with one of the lower indices. You can prove gamma mu alpha alpha being summed over is del by del x mu of log of root minus g. I would need it tomorrow.
Proven in the tutorial.
Huh?
We have proven.
Yeah, proved it in. Oh, very good. Yeah, because that we will need tomorrow.